Welcome to all of the SC attendees joining us from around the world. I am Gabrielle Kotzis, the President of ACM, and it is an honor to be here today.
Good morning, good afternoon, and good evening to wherever you may be joining us. I'm Leila De Floriani, the IEEE Computer Society President, and I'm very pleased to join ACM President Gabrielle Kotzis for this session.
As we do each year at SC, ACM and the IEEE Computer Society will present awards to individuals who have distinguished themselves as truly extraordinary in their accomplishments and contributions to high-performance computing.
We will also have the privilege of hearing a presentation from each of these 16 individuals today and learn more about their research contributions.
First, we would like to honor our 2020 ACM IEEE Computer Society Ken Kennedy Award recipient, Dr. Vivek Saka.
The ACM and IEEE Computer Society Ken Kennedy Award honors outstanding contributions to programmability or productivity in high-performance computing, together with significant community service or mentoring contributions. The award was established in memory of Ken Kennedy, the founder of Rice University's nationally ranked computer science program. The 2020 ACM and IEEE Computer Society Ken Kennedy Award is presented to Dr. Vivek Sarkar, Chair of the School of Computer Science and the Stephen Fleming Chair in the College of Computing at Georgia Institute of Technology. Dr. Sarkar's research in aspects of programmability and productivity in parallel computing, including programming languages, compilers, runtime systems, and debuggers for parallel, heterogeneous, and high-performance computer systems. During his time at IBM, Dr. Sarkar was involved in research projects such as the ASTI optimizer for XL Fortran product compilers, the open-source JIKES research virtual machine for the Java language, the X10 programming language developed in the DARPA HPCS program, and the PTRAN automatic parallelization system led by Fran Allen. Dr. Sarkar has mentored over 30 PhD students and postdoctoral researchers in the Habanero Extreme Scale Software Research Laboratory, first at Rice University and now at Georgia Tech. Researchers in this lab have developed the Habanero C, C++, and Habanero Java programming systems for parallel, heterogeneous, and distributed platforms. Dr. Sarkar is an ACM and IEEE Fellow. He serves on the U.S. Department of Energy's Advanced Scientific Computing Advisory Committee, as well as CRA's Board of Directors.
Our congratulations again to Dr. Vivek Sarkar. What a wonderful achievement. Dr. Sarkar, we look forward to your presentation.
It is truly an honor for me to receive this year's Ken Kennedy Award and to have the opportunity to talk about these topics that are dear to my heart. Today, I'd like to talk about reimagining compilers and runtimes for future high-performance computing systems. So I'd like to start by predictions we had made over a decade ago. This was in the context of two studies. There was the DARPA Exascale study led by Peter Kogi and the DARPA Exascale software study that I had the opportunity to lead. And we were predicting that by the current time frame, 2020, the HPC systems would be extreme scale in nature. They would be built of massively multi-core processors where the performance is driven by parallelism and constrained by energy and data movement, and would also face significant resilience challenges. Now, those disruptions have indeed happened, as I'm going to focus on today, but it's also interesting to note that there's been a disruption at the other end of the computing stack. So bottom up, we have new hardware, new memory technologies, new forms of heterogeneous computing, but top down, we have new application domains, new algorithms, new programming frameworks. And guess where they meet in the middle? Right at compilers and runtimes. And this is one of the reasons why I feel compilers and runtimes are increasing in importance. And this is particularly true as computer architectures become more heterogeneous. In fact, as we look towards the future and approaching the end of Moore's law, we have what has been referred to as a heterogeneity crisis. And in this crisis, we see that the compute capability is increasing, but it does so at the intranode level with accelerators, while the internode scaling stays flat or is declining. So in my opinion, this is another reason why the role of compilers and runtimes now becomes absolutely critical. They have always been workhorse technologies for high performance computing right from the start, but now I believe their role will be pivotal. When we look at current trends in HPC compilers and runtimes, there's a lot of great work going on. As I've listed over here, compiler technologies, different runtime projects, and in fact, many of these pieces of work have influenced my research and my group's research. But I'm going to step back a little and look at what's going on right now from the perspective of one of the great pieces of work in the scientific method, and that's Kuhn's structure of scientific revolutions. And what he said there is, when we are comfortable with an old theory that's well established, has many followers, but some anomalies start popping up, their attempts to address those anomalies by viewing it as puzzle solving in the existing framework rather than looking for a new framework. And I'm going to make the case that we are reaching that point now with compilers and runtimes. So let's start by how we would go about reimagining HPC compilers. I'm going to share a graphic that was given to me by Fran Allen many years ago, and it outlined the compiler structure that she and others used in a project in IBM way back from 1958 to 1962. And the problem they were faced with was they had three source languages, Fortran, Autocoder 2, and Alpha, and two target hardware platforms, the Stretch and the Stretch Harvest. And they were doing all this new work on compiler optimizations, and they wanted to be able to reuse it across these languages and architectures. So they came up with this compiler structure or paradigm with an intermediate language or the IL and IL to IL code optimizations. It's really great to look at the structure because we all know that this is pretty much the same structure we use today. If you look at successful compiler projects like LLVM, they have exactly this form. But all that past work was really conceived of in the days of sequential computing. And I believe that that paradigm is now under siege when we look at our current world of ubiquitous parallelism. Now, it's natural to hold on to the old way of doing things because there's been so much investment in infrastructure for sequential code optimization. And so what we tend to do is, when these compilers have to deal with parallelism in their input program, they start introducing some ad hoc rules. And this is pretty much similar to Kuhn's observation about puzzle solving activities. For example, if there's some parallelization or synchronization construct, the compiler will insert an artificial fence at that point and prevent code motion across that point, even though it might have been legal in some cases with the synchronization. It basically treats the parallel constructs as a black box. So I believe that if we really want to move to a new paradigm that can give first-class support for parallel programs, we really need a new parallel intermediate representation. That IL that Fran had, from around 1960, really needs to be revisited from scratch from the perspective of parallelism. And I'd like to make this case by sharing two examples. The first example is that of integrating user-specified and compiler-inferred parallelism. Right now, these are two independent tracks, and they really have to come together. So when they do come together, what we're conceiving of is a system where the input is a parallel program with all the logical parallelism. It's not the case where the programmer is directly telling the compiler which constructs to actually run in parallel. They're indicating which parts of the program could potentially run in parallel, what is the partial order, in terms of the logical ordering in the program. And we then need new program analyses that can understand the parallelism specified by the programmer, but also infer new parallelism as compilers have done in sequential code, and combine those two in selecting program transformations that can generate an optimized parallel program. And as we'll see, one new addition that would be needed is this notion of happens before dependencies, which are quite different from the sequential dependence analysis that we've used for many decades. So here's a very simple example to illustrate the point. We have an OpenMP loop, and the programmers helped us out by saying that the outer I loop is logically parallel. And in fact, OpenMP now has this new loop pragma that makes it easier to communicate this fact. But the programmer hasn't said anything about the J loop. The J loop, on the other hand, is something that the compiler can infer to be parallel. But depending on the language, for example, if you have arrays of arrays for multi-dimensional arrays, a C compiler may not automatically be able to infer that the I loop is parallel because the two row pointers may, in principle, point to the same row. So here we have two pieces of information, one from the programmer indicating that the loop I can be parallel, and one from the compiler indicating that it's legal to run the J loop in parallel. So the formal background there for this static happens before dependence analysis is to extend what we've done before for dependence analysis in sequential programs, but relate them to the partial order inherent in the parallel program. And once you have this framework, you can actually enable the compiler to perform new kinds of transformations that it may not have been able to do when stuck in the old paradigm. So as an example, if we have this for loop where statement S1 is assigning to an array and statement S2 is creating a parallel task that reads from the same array, if the compiler cannot analyze the subscript functions f of I and g sub I, it would say that sequentially it's illegal to distribute the loops because you're not sure it's safe to wait on the reads till all the writes have been performed in S1 because it's possible that the value being read in S2 would be overwritten by some iteration in S1. However, if it was written with this task parallelism, the compiler could reason that the distribution is perfectly legal because according to the task parallel happens before relations, it's completely fine for all the async tasks to wait till after all the instances of S1 have completed. So this is just a simple example to illustrate the point. And the key theoretical idea behind what's going on over here is that we can take the conservative dependencies analyzed by the compiler, such as the compiler not understanding that the I loop is parallel and assuming that iterations of the I loop depend on each other, and we can intersect it with the happens before relation provided by the programmer. And in this case, where they said that the I loop is independent, but they didn't say anything about the J loop, which is sequential by default. And the intersection gives a reduced set of dependencies, which is a set of dependencies that need to be obeyed for code transformation. In this case, it happens to be an empty set, but it enables more flexibility for code optimization. And when we evaluated this approach, we compared 3 different versions of a set of benchmark programs. So in this slide, I'm showing you the comparison of some task parallel programs. And we have the originally OpenMP version from the Castor suite. We have the green bar, which is you take the original code and the sequential version and let the compiler automatically parallelize it using the best of today's technologies. And the gold bar is what we get by this intersection approach to get the best of both worlds. And we see that even though sometimes the original OpenMP may do better than the automatic parallelization or vice versa, combining the two gives significant improvements. This can also be seen for another set of benchmarks that are more loop-oriented, the Rodinia benchmarks, and we see a similar trend. And in no case do we see the combined approach doing worse than either of the explicitly parallel OpenMP or the automatically parallelized versions. And I just want to comment that even though I focused on data dependencies over there, this idea of a parallel intermediate representation can encompass both data dependencies and control dependencies. We've had the notion of a program dependence graph for many decades now, and the fact that it captures all the ideal parallelism. But we can actually convert that ideal parallelism into whatever useful parallelism we might like in our final program, and use a unified parallel intermediate representation to represent sequential programs, program dependence graph, and anything in between in terms of the parallelism that the compiler would like to use. So the second example that I would like to use relates to memory movement optimizations for heterogeneous computing. So one of the big challenges for programmers, both from productivity and programmability viewpoints with heterogeneous computing, is it's not just about offloading compute, it's also managing the data and managing the copies of the data on a heterogeneous device and a host CPU, for example. So the OpenMP specification has some target mapping clauses, and the simplest one to use is when you just say you're mapping a variable like this map of A, where by default the compiler would generate code to transfer array A at the start of the kernel to the device, let the device update it, and then transfer A back, and the second kernel transfer it again back to the device. Well, a compiler is actually able to optimize the data flow for these data transfers and determine which data transfers can be redundant. And actually OpenMP has a way to specify that, for example, in the second kernel, you don't need a to map. You don't need to transfer array A again from the host to the device, because the version on the device is still the latest version to use. However, at the end of the kernel, you do need to transfer A back to the host because it is being used on the host after that. And what we've seen with these optimizations is here, because this is for heterogeneous programming, these results are for some spec Axel benchmarks, 4 of them, and on a platform with a multi-core CPU and GPU accelerator. And the performance improvement we are seeing is really the improvement from optimizing these data transfers. And as you can see, there are very significant improvements going to about a factor of 9. So with that, we can see that compilers can indeed be reimagined from the viewpoint of explicit parallelism and also heterogeneous computing. Let's take a look at how Hpc runtimes can be reimagined. So as with compilers, runtimes have a long tradition of foundations that were built many decades ago. In this case, these are foundations that date back to early work in operating systems that introduced threads, locks, inter-process messaging, and so on. And they actually were good enough for our past HPC systems. We could roll synchronizations on top of these primitives and enable things like SPMD execution models. But now, when we look at the extreme levels of heterogeneity and distributed compute and data that we expect in future HPC systems, there are going to be major challenges. So in terms of performance, synchronous computation is going to be very challenging, because with heterogeneity, you'll have devices running at different clock speeds, you'll have long latencies. So really, computations and data transfers need to be initiated asynchronously. And reasoning about just programs with threads and locks were hard enough. Reasoning about all the additional coordination that's needed for heterogeneity is going to be even more challenging. And so that's another reason why we need new primitives that would support compositional reasoning and invariance. So one approach that seems to be now picking up momentum is that of revisiting the basic core idea of data flow computing. But here, rather than viewing it as a way of designing computers, we're using it as a way to provide the foundation of HPC runtimes. And the observation is that any time in a runtime, if there's a blocking operation, that synchronization can be replaced by an event-driven continuation task. So if you have fork join and there's some code waiting at the end of the join, that code can become a new task that is activated by the event that satisfies the join. The same applies to critical sections, transactions, futures, and so on. And in that way, you can have what's called a cooperative runtime, where these continuation tasks and new tasks all get scheduled as their inputs and events get ready. So let me share some examples where this data flow approach can really be promising as we look towards the future. So one of the trends that we have to cope with in our current and future HPC systems is that of integrating message passing that we've had for many decades, most notably with MPI, integrating that with the increasing levels of task parallelism and heterogeneous parallelism within a node. And here's a data flow way of looking at how that integration can be done. What we have over here in this very simple example is two non-blocking MPI operations, a send and an ISend and an IReceive. But the IReceive has a request that is set when the receive is complete. And what we're going to do in integrating the two using data flow foundations is use that request as an event for an event-driven task, which is in line 2 for S2. The async await says that S2 can only be ready to execute when the MPI request is ready. And S5 is something else that can run in parallel with all the computations specified in lines 2, 3, and 4. Then we have a finish scope, and S7 is something that can only execute after everything in the finish scope has completed. So on the right, we see what really looks like a data flow graph or a dependence graph to capture these semantics. We have the F1 start and the F1 end that demarcate the finish scope. Within that, we have the ISend and IReceive that can logically proceed in any order. We have the statement S5 that could also execute while the non-blocking sends and receives are in progress. And we have statement S2 that must wait for the IReceive to complete before it can execute. And we have S7 that waits for everything in the finish scope. So now we can see that each unit in this graph can be a task in our cooperative runtime, and there's absolutely no need for any waiting operation over here. To implement this, you can take a state-of-the-art tasking runtime, such as the work stealing runtimes, and extend that with support for communication. So here I've shown a communication worker, and statements like ISend and IReceive can be offloaded onto the communication worker. And when a communication task is completed, any new computations that it enables would be pushed into this continuation queue, which can be stolen by other compute workers as usual. So this is a very tight integration between the two that's enabled by data flow principles. We've actually used this kind of integration to also implement an actor-based programming model. I'm showing this for a very simple example where ideally what you want to do in a global address space is update a global table at different indices. So some of these locations may be local, some may be remote. What I'm showing below on the left is a version with a highly optimized message passing library called Conveyors. And in this library, the expert programmer has controlled where to call push, pull, and advance, where push is accumulating messages into buffer, pull is extracting messages from a buffer, and advance is causing the communication to progress. The selector version, which is an actor with multiple mailboxes, just has this non-blocking send operation where like an active message, and where the action to be performed when the message is received is specified as C++ lambda. And even though this is a very simple example of incrementing one element of a distributed table, it could be more complicated. The body of the lambda could actually contain additional sends with replies and so on. And what we see is that if we take a standard implementation of the ideal version, in this case implemented with OpenSHMEM and atomic get put primitives, that's the OpenSHMEM AGP version, and we look at the execution time for two mini apps, topological sort and triangle counting. The blue bars show the execution time, and for the orange and the gray bars, we have the conveyor and the selector version. So the conveyor is one where the programmer is managing everything at a very low level of detail, getting great performance, but not with high levels of programmability or productivity. The gray version, we would argue, definitely offers more programmability and productivity, but interestingly is very close to the conveyor version and performance. And there's a great opportunity for future research for compilers to automatically take that ideal version represented by the blue bar and generate the actor version as code. I think this is a bridge that compilers could easily span in future research. Another example that I'd like to pick for runtimes is that of hybrid scheduling for heterogeneous actors. So now we're talking about a model where you have compute steps and you may have multiple versions for each step. For example, versions that could run on a CPU, GPU, or FPGA. And we want to use the same data-driven approach of cooperative scheduling. And this has been demonstrated by using what we call a proxy worker, because some of these devices, like an FPGA, does not have the logic to be able to support a runtime, a work-stealing runtime. So the proxy worker plays the role of supporting the work-stealing runtime and determining which tasks should be offloaded to the device. Like here you see this queue offloading tasks to the GPU device. And if that queue gets too large, other devices could be stealing work from this queue. And when that work on the accelerator is completed, then its continuations are pushed in the red queue and are available to be stolen by other workers. And this goes beyond GPUs and FPGAs. It's also been demonstrated for other accelerators such as digital signal processors. In this case, there was an interesting opportunity where the hardware actually had queues for communicating between the ARM CPU cores and the DSP processors. And these hardware queues worked very well from the perspective of supporting work-stealing runtimes. So with those examples of how we could reimagine compilers and runtimes, let's talk a bit about the implications on future programming models. So here I'd like to get back to the two ends of disruption on the compute stack and look at the disruption that's coming from the top end. And let's look at the space of all HPC developers. We can categorize them as HPC experts. These are the real ninjas who could, for example, program at the conveyor level I mentioned. And many of the features in today's HPC programming models are really only accessible to them. We have library and framework developers who really want to map and tune algorithms that they receive from domain experts onto different platforms with performance portability. And then we have the domain experts, which far outnumber the library and framework experts, who in turn outnumber the HPC experts. And they're the ones innovating and need programming models that can express new parallel algorithms for future HPC systems. Of course, the library framework and the HPC experts are innovating at their levels too, but in terms of exploring the application domains where we can use high performance computing, the domain experts add a key value. So another motivation for reimagining compilers and runtimes is how can we improve productivity and programmability for these domain experts by new approaches to compilers and runtimes. Now, one aspect that I alluded to earlier was semantic guarantees. As hardware is getting more complex, we need ways in which we can reason in a compositionally way about the semantics of different subsets of parallel constructs. So, for example, there are results that show that if you're in a subset that has certain task parallel primitives, notably task creation like async and task termination like finish, then they're guaranteed to satisfy the serial projection property, they're guaranteed to be deadlock free, and also satisfy this very interesting property called data race freedom implying determinism. And if we add futures to this, then we don't get automatic deadlock freedom. We have to also have data race freedom as a precondition for deadlock freedom. If we add phasors to this set, then we lose the serial projection property and so on. So this compositional reasoning allows us to navigate and say, okay, if a domain expert is working with a certain subset of parallel programming primitives, they can have automatic guarantees about the safety of the code that's derived from the application that they write. So one of the points that's been made recently is that it's really important to see how to bring high performance computing to high productivity languages like Python, given the large numbers of Python programmers analogous to the domain expert slice in the inverted pyramid. In fact, if you look at GitHub projects, JavaScript and Python are the two top languages used across all GitHub projects. So to investigate how compilers and runtimes can contribute to Python programmers, we have a project that we call Intrepid, where we work with a subset of the Python language that just requires type declarations for function parameters and return values. And certain functions of the Python program can be annotated in this way and then passed through our compiler toolchain, which can generate optimized C++ code, as well as generate Python code, which can interface with task-based Python runtimes. In our case, the task-based runtime we are using is the Ray runtime that allows tasks to be distributed across multiple cores and even multiple nodes in a cluster, which is a major challenge for Python programmers. It's hard enough for them to do multiprocessing within a single node. To actually use multiple nodes often means combining Python code with MPI or a similar alternative. So for the toolchain where we generated C++ code, I'm sharing some improvements that we got relative to the original Python code. And this is compared with two existing toolchains that Python programmers use as compiler techniques to improve performance. One is Cython and the other is Number. Number in particular is a very robust just-in-time compiler that can support a wide range of Python functions, and actually reminds me of a lot of the work we did a long time ago in the JIKE's RVM project when we were doing dynamic and adaptive optimization of Java programs. But here, what we have in the Intrepid version is generation of C++ code for these individual Intrepid functions, and we see very significant performance improvements, an order of magnitude, as you can see in the green bars, even going up to 3 orders of magnitude. So this is one way in which compilers can really help with productivity and programmability by bringing this performance to Python programmers. Another way is through runtime, and here I'm just showing you how a compiler could automatically take some code. In this case, it's signal processing code for the space-time adaptive processing application, and identify tasks that can be run really as futures, where their tasks are spawned, and then you synchronize on the tasks later in line 18 on the right-hand side. So with this distribution, we actually can get very interesting performance, not just on a single core as we saw earlier, but here we're talking about using 1 GPU to begin with, where it's 172 times faster than the original NumPy CPU version. But through the use of Ray's task runtime, we can actually use 6 GPUs in a node and seamlessly use GPUs on multiple nodes in a cluster, which, as I mentioned earlier, is a major obstacle for Python programmers. And so here again, we are seeing 3 orders of magnitude performance improvement with just using 4 nodes and 6 GPUs per node. So with that entire context, I'd like to take a few minutes to reminisce and acknowledge everyone who's contributed to my career. I'd like to start with my mentors, my PhD advisor, John Hennessy. He was an amazing role model, and even though he's extremely busy, he's accomplished so much himself, I still turn to him when I need to make a major career decision. Many people know him, of course, for his amazing Turing Award-winning work related to computing architecture, but he was also a leading compilers researcher and got me started in the compilers area. Related to compilers, I would also like to acknowledge my mentor at IBM, Fran Allen. She was a fearless leader of the Ptran group, and it was a sad day for all of us in the group when we learned of her passing away earlier this year. She would definitely have encouraged us to reimagine how we do things with compilers and runtimes, and to embrace revolutionary new approaches. I would, of course, like to take a few minutes to talk about Ken Kennedy. He was the kind of person who was where he was a mentor to almost everyone he interacted with. In my case, when I was a junior researcher at IBM, when we met, he would encourage me on my various research directions, many of which actually overlapped with research problems that he was looking at in his group. Around 2005, he started talking to me about whether I should consider academia as a career option, and that led to my joining Rice University in 2007. Sadly, that was a few months after he had passed away earlier that year. And recently, I find I'm reminded of him regularly because I teach a course based on his textbook using slides that he created. And it's really great for me to share anecdotes about him with my students in the class when I do so. Ken was truly a gentleman and a scholar and an amazing mentor, and it's so great that we have this award in his honor. Finally, I'd like to acknowledge all my collaborators. Here's a photo of some of my collaborators at IBM who worked on the JIKES Research Virtual Machine project. There were, of course, many other collaborators at IBM. My collaborators at Rice University, and my current collaborators at Georgia Tech, and of course, all the past and present members of my lab. I love the teamwork and all the research contributions. This is a graduation photograph from 5 years ago when we had a bumper crop of 5 PhD students that year. So to conclude, I think we can embrace a phrase that I recall Ken sharing with me, and that is to let's aim for abstraction without apology. Let's talk about this holy grail where a domain expert can specify their application and their algorithm declaratively and get real semantic guarantees despite all the complexity in the underlying hardware, where the compiler can generate multi-version code and reason about explicitly parallel code to ensure that we get the best performance, and where the runtime can schedule compute and data movement tasks in an optimized way across very distributed and highly heterogeneous processors in an HPC platform. So I really believe that exciting times are ahead for us, with many changes afoot in high-performance computing, especially from the software perspective. We have new classes of applications like deep learning and data science and real-time applications. We have new languages for high-performance computing being explored. We, of course, have a proliferation of innovative new hardware components as we grapple with the end of Moore's law. And I really believe that reimagining compilers and runtimes will help transition us to this brave new world where we have the holy grail with productive domain experts leveraging the best of what future HPC systems have to offer. Thank you.